Okay, so this is the last PowerPoint of the semester. Yoo-hoo! Been a crazy one. Um, so the last PowerPoint had to do with finding the bonding structure, and I sent you out a worksheet and try to figure out some on your own. Uh, this lecture will both the Chem 110 and 121 will be using lots of it together, and it'll be separate uh, at certain points, but I'll split that off. But and I will send out on the announcements yesterday or on Monday. I I told you what the plans are, and I'm going to kind of stick to them. I'm a little bit behind already because of coming up with this PowerPoint, but we'll get everything done. Just like I said, by next week, and we'll all be done here. And I'll send out the answers to that bonding. I know it's difficult. I'd rather be with you guys, showing you how to do it, walking around and seeing how well you're trying to, get doing it right, and so forth. But so we can't do that. So the answers that I send you, I will try to detail them as much as I can so you can follow along and figure out what you did right and what you need to work on. Okay. So the same thing will go with this. I will send out another worksheet that has to do with this. Um, there's a lot of information here, and when it comes down to it, I will uh, there on the worksheet you will get an idea of what you need to distill out of this. Okay, so what we have here, and so so now what we want to do is see what this leads to. Okay, so after we find the bonding structure tells us the connectivity of the atoms in the molecule. It tells us the number of the bonds and lone pairs associated with each atom. This structure, bonding structure, is a two-dimensional structure. Basically, just shows us this connection, but it doesn't give us the three-dimensional structure. Okay. When we draw the bonding structure, it is easy to think that with the way we draw it on the flat surface is what it looks like. Okay, but it isn't. I remember when I was taught this years ago, I thought when they drew it up on the board, the shapes, the way that they drew it, that's the way I thought these molecules were. Okay, these molecules and every molecules are three-dimensional. It only makes sense. I mean, everything around us is three-dimensional. Therefore, the things that are made of it have to be three-dimensional. So we have the bonding structure. Now what we want to do is, from the bonding structure, can we actually see what it looks like? What can we figure out what it looks like in 3 dimensions? Okay. So again, back to bonding structure. Let's take a look at water. When we came up to it, we kind of came up with this structure right here. But I told you is we'll get to this in a little bit. You could also draw it like this, or you could draw it like this. It really doesn't matter. All you have to make sure to show is the hydrogen. The oxygen has two hydrogens attached to it, and there's two lone pairs. Okay, any of these would do. Now, technically, we usually either draw it like this or this, but there's no reason why we couldn't draw it like this, because actually this might be how we see it in 3 dimensions. Okay, there's no perfect way to draw, but we prefer to probably draw it this way, at least to start out with. Okay, now what we're going to do is try to figure out what water looks like and other molecules, simple molecules, look like in 3 dimensions. Once you understand the three, simple molecules, you can figure out shapes of even more complicated molecules. All right, so what we want to do too is determine what the three-dimensional structure of covalent molecules. And what we're going to start out is beryllium dihydride. And we're going to come up with its bonding structure first. So this kind of review of what we just went over. So first of all, count how many valence electrons. Beryllium has 2 and each hydrogen has 1. So it'll be 2 plus 1 plus 1 is 4. The skeletal structure is HBEH. Put the beryllium in the middle. Now, hydrogen's on the outside, so make sure it gets the number of bonds and lone pairs that it usually gets, which is 1. You do that for both of them. So now what you do is you count the number of dots. Each dash is equal to 2, so 2, 4. And if the number of dots is equal to the number of valence electrons, you're done. Okay, so this is the bonding structure. Again, notice this method is you don't really care even what beryllium is, because it'll all work out. Okay, so now let's take this and try to figure out what it looks like in 3 dimensions. All right, okay, so first of all, now what? Let's try to visualize a little bit more. So this molecule, each atom has electrons on the outside of it. Okay. All right. And electrons repel each other. Okay. So if you had two negative charges coming close together, they push away a charge. So now what we're going to do, again, we're going to try to make this, think of this as 3-dimensional. Let's allow the hydrogens to swivel on the bond between the beryllium atoms. So imagine in 3, so this is a ball, this is a ball, and this ball, and this is some sort of rod, and this is some sort of rod. And what it's allowed to do, it's allowed to swivel around it. But, you know, we can't show it, but it's allowed to swivel in and out of the screen as well. Okay. All right. Now, if for some reason this hydrogen starts to swivel, as it swivels, okay, and as it gets close to this hydrogen here, the electrons on both of the atoms are going to push each other back. For instance, like this. All right, so let's say this hydrogen starts to move just randomly in this direction. Well, if it starts to get too close, it'll get pushed back, okay? All right, but now let's say it tries to swivel this way again. And again, it gets too close and bounces back. So in the long run, the two atoms, the two hydrogen atoms, want to be as far away from each other as they can to reduce the repulsive effect. Okay, this is called the valence shell electron pair repulsion theory, or VSEPR. The resultant final structure looks like this, kind of, okay? And that's because we have to think of this as 3-dimensional. Okay, so this would be looking at it, let's say, from the front, okay? Now, if you were to take it out, if we looked at it a different way, maybe from the side, what you're going to see is like this. Okay, so it looks like a line from one view, but if you look on this view, it looks like everything's all bunched up. Okay, right, or even from an angle, you might see it like this. Okay, where this hydrogen is the closest one to, and this one's the furthest away, and this one's in between. So the one thing that's true about all of these is that these hydrogens and beryllium are all in line with each other. Okay. Right. The key thing to realize is we really can't draw this thing what it looks like in 3 dimensions. That one I just had, the angle one, kind of gives you the best view of it. But you just got to think. If you ever see this molecule, you got to think that it's linear. Now, so this molecule is called linear. This shape is called linear. And the thing that makes it linear, the way that you can determine if it's linear, is if it has 2 atoms connected to the center atom and there's no lone pairs on the center atom. Okay. All right, now let's go to another one, BH3. So, right, so the number of valence electron is 3 plus 1 plus 1 is 6. So this skeleton structure give hydrogen the outside atom, number of bonds and lone pairs. That's hydrogen 1 1 1. Add them up. 2 plus 2 plus 2 is 6, and 6 equals 6. So this is the bonding structure. And remember, it doesn't matter how you draw it. You could draw it this flipped or sideways or whatever. Okay. Okay. Now let's try to figure out what it looks like in 3 dimensions. All right, again, we're going to allow the outside atoms to swivel, so the hydrogen are going to start moving around. And say this guy starts to move up and it smacks into this hydrogen, well, it's going to be pushed back, okay? And then let's say this guy switches up, it's going to be pushed back. Eventually, all the atoms are going to repel, try to get as far away from each other as they can, and they're going to end up having this shape right here. At least from the front view, okay? Now notice the shape looks like a triangle. And that's how we're going to name it. But there's another element to that. And that's because I'm from the side view. So you take this guy, flip it on the side. You're going to look as though all these guys, all these atoms are in the same plane. So what we call this shape is trigonoplanar. And a way to identify if you have a trigonoplanar is if the center atom has 3 connections, 1, 2, 3, and there's no lone pairs on that atom. All right, now let's go with 4 connections, like methane, CH4. We did this already in the bonding structure. This is its bonding shape. Turns out it doesn't look like this thing at all, okay? So if we let these hydrogens flop around, swivel all around in 3-dimensional space, this is 2-dimensional. If this was 2-dimensional space, this is what the molecule would look like. But in 3-dimensional, what happens is all the hydrogens can push out from each other, in and out of the plane. And so what you end up actually is get something like this, which is really hard to draw in 2 dimensions. So one way to think of this is like a tripod with an H coming off. Okay, this particular shape is called tetrahedral. It has 4 connections on the center atom and no lone pairs. Okay, all right. Now what we're going to do is look again at another molecule with 3 connections, just like we did BH3, the one that was trigonoplanar. But what we're going to do is this molecule is going to have a lone pair on the center atom, like ammonia. Okay, we came up with the structure before. We came up with this. And if you let it swivel, okay, it's going to end up looking like trigonoplanar, okay? But the problem is these lone pairs up here are electrons. And what they're going to do is repel these hydrogens. And so they're going to push these hydrogens all away from each other. And so if you looked at it from the side, it's not a straight line anymore. It's actually kind of at an angle here. Okay. So what does this look like in 3 dimensions? Well, it kind of looks like what we just had with methane. But what we do is replace one of the hydrogens with a lone pair. And notice it's still going to have, so this shape right here is the triangle. Okay. Right, but you could see that in 3 dimensions, if these 3 hydrogens are sitting on a flat surface, this guy is above the surface, and it kind of looks like a pyramid if you connect all these sides here. And so we call it trigonal because of these H's. The front view would form a triangle, and from the side it would be a pyramid. And the way you tell is it has 3 connections, like trigonoplanar, but it has 1 lone pair. So trigonoplanar and trigonopyramidal are similar. They both have 3 connections to the center atom. The difference is the pyramidal has a lone pair. Okay, finally, let's look at water. So water has 2 connections, just like BH2, but it has lone pairs. Okay, now the way you draw it like this, it looks linear, like the beryllium dihydride. But if you let it swivel and these hydrogens find in the right spot, it's gonna they're not going to be in a straight line anymore from the side. Okay, it's going to turn at these come into an angle. And if you look at it three-dimensionally, it kind of looks like what couple that we just looked at. So here, so this is like this side up here, and if you turn this on its side, it would look like this. Okay, but three-dimensionally, this kind of gives you the view. Is that you have these two guys coming off the oxygen, and then you have these guys coming off in a different plane. So again, it kind of looks like a tripod, but one of the legs is lone pairs. This shape is bent, and you know if you have bent if there's two bonds and two lone pairs. So if we put this together, this is a chart, making it into a chart. This is what we kind of get, okay? So these are the number of connections, and these are the number of lone pairs to the center atom, and these are particular shapes. And here's our examples. Now, one of the things I want to clarify, this is kind of messed up over here, but you'll see in a second, is connections do not necessarily mean bonds. For instance, carbon has 4 bonds, but it only has 2 connections. So the connections can either be single bonds, or it can be like double or triple bonds. So carbon dioxide in this case has 2 connections, no lone pairs on the center atom, so it's going to be linear. Okay. One that we did in the last PowerPoint was COH2, and it sort of looks like this. There's center atom's carbon, and there's an oxygen and 2 hydrogens. That would be it has a double bond, single bond, but it only has 3 connections, so that would be trigonoplanar as well. And one of the things that you're going to have to do is the structures that you came up with for your homework. For the last slideshow, you're going to have to figure out the shapes of those molecules as well. Okay, so now we're going to polarity, and this will be both in 110 and 121. So let's look at a hydrogen molecule, H2. The bonding structure is HH. We learned this previously. Now, all atoms have some ability to pull electrons toward themselves, we learned. And this ability is called electronegativity. So both of these, so you have this shared pair here, and both hydrogens are pulling on it, okay? Now, we learned that electronegativity is dependent on size. Smaller atoms have higher electronegativity, and so forth. Okay, so what we want to do is see what happens to these pair of electrons as these hydrogens. So it's like a tug of war. So you have this hydrogen pulling on it, and this one, and here's their electronegativity, and these are kind of like forces, not technically. So this is pulling on it with 2.1 in this direction, this is pulling 2.1 in this direction. You can see that they cancel each other out. So overall, those electrons just stay exactly where they are. So these electrons are equally shared between both hydrogens. Now let's say I replace one of the hydrogens with fluorine. Fluorine has a higher electronegativity, so I'll draw an arrow to represent that. Okay, and now what we do is we add up the 2 arrows. Okay, this 2.1 is going to subtract from the 4 going in this direction, but it's going to leave 1.9 still going in towards the fluorine. That means that overall, these 2 atoms, is that the fluorine is going to have more of the electrons, the shared pair, pulled towards them. Okay. Now you won't have to figure out these numbers, okay? Just to show you how it works here. Okay, so Maybe for 121 I will. So, but not for 110. So, overall, what you get is that there's a unequal sharing of electrons, where fluorine has more of the electrons than the hydrogen. So fluorine actually becomes a little bit more negative because it's got more negative pulled towards it. And hydrogen's lost that negative and therefore could become partially positive. And so what we do is we can draw these two symbols here. This means partial positive, this means partial negative. Now, well, the way you could draw it is you're going to have this arrow showing which way the direction of the electrons being pulled towards the fluorine, and the plus down here means that this side is more plus. Okay. Now, another way to kind of think about it is that it's kind of like a magnet. It has a plus pole and it has a minus pole. Okay, so it has a negative end and a positive end. Right. This kind of molecule is called a polar molecule because it looks like a pole. It has a plus and a negative end, sort of like a magnet. Like just instead of a north and south pole, it has a plus and minus. So we call this a polar molecule. A polar molecule is when there's an unequal sharing of valence electrons. When you have a sharing, equal sharing, like in the previous H2, that's called a nonpolar molecule. Right, so let's look at some more examples. So let's look at BH2. And what we kind of want to do, and it's more complicated than this, and I don't want to get into it. I would like to, but there's more to it than this. But we're gonna sort of just distill down what we need to know. And hopefully people that go into this deeper will see what I mean. Essentially what I'm saying is that what we're going to do is look right now at the polarity of a molecule, but there's also polarity of bonds. Right now we're just going to end up looking at the polarity of a whole molecule, but the polarity of the bonds are going to help affect the polarity of a molecule. Okay, so like in a previous example where the two hydrogens are pulling on, you have the two hydrogens pulling on the beryllium in equal force, and therefore the beryllium, in a sense, is equally shared. So this would be a nonpolar molecule. And again, let's replace one of the hydrogen with fluorine, and we'll get an unequal share of electrons towards the fluorine, and so this would be a polar molecule. So the top one is nonpolar, the bottom one is polar. And what determines the polarity of these molecules is the difference in the atoms that are attached in the molecule. All I had to do is change this guy over here or this guy over here, and you could change the polarity. Okay, so this polar molecule, and you kind of can draw like this, plus and a minus. You don't have to put these guys, these are deltas, you can just put plus and minus. But it's not a full plus, it's partial plus and partial minus. All right, so what we have is this thing called polarity. And polarity is the overall charge distribution of charged electrons on a covalent molecule. So how are the electrons shared on this molecule? If they're unequally shared, like in this case, we call it a polar molecule. If they're equally shared, like we saw with two H's attached, that's called nonpolar. And again, what makes this happen, the polarity of this, what determines the polarity is the atoms attached and their electronegativity. Okay, now so let's look at water now. So set up, draw it, and if you notice, it kind of looks like what we saw with beryllium dihydride. And it looks like this molecule should be nonpolar. But the key thing, it's not true, is because water is not linear. From this view, okay, all right, it looks like they cancel out. But if we turn it on its side, we get this, okay? And this is what determines if it's polar or not. Okay, so what I'm do here is I'm going to draw, and this, if this goes over your head, that's fine, but hopefully some of you will be able to pick it up. And it relates to vectors, if anybody's vectors, but hopefully you maybe get to get an idea how it works. Okay, so and I'll try to describe it in more an analogy in a second as well. So so here's your oxygen, and your hydrogens are pulling on the electrons, let's say, okay, down, not straight across anymore, but down. Now one way to kind of think about it is like, suppose you have, in first case with beryllium dihydride, you have two people equal heights pulling, same height as you, and they're pulling on your arms, okay, and they have equal strength. Okay, you're not gonna go anywhere. Okay, but now let's do this. Let's have two little people, maybe about 2 feet tall. Okay, have them pull on your arms. Are you gonna move then? Okay, yes, you are. All right, you are gonna be pulled down. Okay, because they're not pulling straight out from you anymore. They're pulling straight out, but they're also pulling down. So overall effect is you're being pulled down. Okay, so the way that you can draw it out is you have these two guys pulling on you, and there's a part that's pulling straight across. Okay, they're both pulling out from you, but they're also both pulling down from you. Okay, the pulling out parts are going to cancel out. Okay. Okay, but the pulling down parts are actually going to add up because they're both pulling down. And so overall, the electrons are being pulled down or up, okay, depending on the strength, okay. So overall, this molecule is not nonpolar because the electrons are actually being pulled down, or well, actually up, but the way that we drew it here, they're being pulled down. So what made this a polar molecule was not the atoms that were attached, but was the shape of the molecule, the bent shape. So water basically has this. It has a plus down here and then minus up here. Okay. Right. So two reasons why that determine polarity of molecule. One is atoms that are attached, and two, the shape of the molecule. Now, what I want to do is I want to give you a shortcut, a way that you can identify if a molecule is polar or nonpolar. And there's many shortcuts in chemistry. This just gives you an idea, and what we're going to do is come up with two different ways to identify if a molecule is polar or not. It doesn't tell me the reason, it just gives me a trick to figure out. Okay, and this tells you the two things actually determine. Now the tricks. Trick number one. If you're given a bonding structure, if the center atom of a molecule has more than one thing attached, okay, in quotation, it will be a polar molecule. Or its converse, if the center atom has same things attached, it would be nonpolar. So let's see if this works. So let's look at BeH2 and BeHF. Okay. So in the case of BeHF, right, it has two different things attached to the center atom. Okay, there's an H and an F attached to it, and we found that it was polar. Okay, so it has different things attached and it's polar. Okay, so it turns out that is true. Okay, all right. For BeH2, okay, the beryllium had the same atoms attached, two hydrogen, and it was nonpolar. So, same atom, same things attached, nonpolar. Different things attached, polar. Okay, seems to be working. Now let's look at water. H2O. At first glance, it looks like water has the same things attached to the hydrogen atoms. But notice that also attached to that oxygen, are lone pairs. So that's why I put things in quotation. The things could be either lone pairs or atoms. So so the oxygen has more than one type of thing. It has lone pairs and it has bonds. We found out that it was polar, and guess what? It has different things attached to it. Okay, so what you're going to have to do with the bonding structures that I gave you for homework, you're going to have to first figure out what the shape of them. And then what you're going to have to do is figure out the polarity of the molecules using this technique. Okay. All right, so let's go over some. And so these will be some of them. This structure here is nonpolar. Notice the carbon has all four things attached, same things attached. Ammonia, okay, it has bonds and it has lone pairs attached, so it's polar. Okay. Carbon dioxide is nonpolar because it only has oxygens attached. This guy is polar because this carbon has oxygens and hydrogens attached. And this molecule is polar as well because this carbon has nitrogen and hydrogen. Now, when we're looking at the lone pairs, you're just looking at the lone pairs on the center atom. These guys out here on the oxygens or nitrogens have no effect on the shape or the polarity. Okay. So these lone pairs here determine the shape. So it has two different things. It determines the shape and the polarity. So the shape is trigonal, pyramidal, and the polarity is polar because it has different things attached to the center atom, lone pairs and bonds. This is trigonal planar because it has three things attached and no lone pairs. But of those three things, they're different. So this is going to be polar. Okay, trick number 2. The second method is if you're only given the molecular formula specifically for organic molecules. And what is an organic molecule? Well, if you take 111, you'll hear about these, or if you go into organic chemistry, but these kinds of molecules have lots of carbons, hydrogen, oxygen, nitrogens. So the trick is this. If the ratio of carbons to oxygens is where there are more than 3 carbons per 1 oxygen, the molecule is probably nonpolar. So a couple examples is this. So here's glucose, C6H12O6. The ratio is 6 carbons to 6 oxygen, which is the same as 1 carbon and 1 oxygen. And that the ratio is less than 3 to 1, so this is a polar molecule. Right, here's a molecule. This is a molecule of, this would be a fat molecule. You don't have to know that, but here's a formula. The ratio is 18 carbons to 2 oxygens, or 9 to 1. So this is greater than 3 to 1, so this is a nonpolar molecule. Now, if you take 111, you'll be seeing a lot of this, and it's really important in terms of polarity. Okay. Now, this next section is this could be for 110. And if 121, you see this, that's fine. You can ignore it, or you can just pay attention and see and listen to it, okay, because it's interesting. So let's look at, we're going to look at molecular interactions. And what molecular interactions are, the interactions between molecules, okay, like 2 water molecules interacting or so forth. Let's look at different states of matter first. It's gas, liquids, and solids. And this should be solid, not salt. And see what causes them to be like they are. Okay, a gas is when none of the particles interact with each other. Now, some of them might, but most of the particles in a gas are just banging around, hitting the walls, hardly ever bumping into each other. The reason why they don't interact because there's no close attractions toward each other. They're just not. They don't. There's no way for them to stick. Okay, to each other. On the other hand, on the other end of the spectrum, we have solid. In solids, the particles are fully interacting with each other as much as they can. The reason they interact is because there's an attraction between the particles that holds them together. And then in liquids, you have particles that interact like a solid, but not all of them are interacting efficiently and completely like in a solid. So really what you want to do is just kind of look at the two spectrums, okay, of gases and solids. Right, before we go on and talk about molecular interactions, let's talk about interactions between the parts of an ionic compound. So all ionic compounds like table salt, which is NaCl, are solids, forming very intricate crystal structures. The reason why they're solids is because there's attraction between the positive ion and the negative ion. This is called an electrostatic attraction, and it forms between ions, and so this is called an ionic bond. So electrostatic attraction between positive and negative ions forms an ionic bond. Okay, so this holds together a molecule of sodium chloride. This is not a molecular interaction. This is an atomic interaction. Okay. But we're going to see that's something that's, when we talk about molecular interactions, there's some similar things that happen. Right, so what we're going to do is looking at interaction between polar molecules, then we're going to look between nonpolar, and then polar, nonpolar. So we want to look what happens when we bring two polar molecules close together. Will they attract, maybe like ionic bonds, and thus form a liquid or solid? Well, let's take a look at water. So water, we found out, has a plus and minus end like this. Now you could draw it kind of like a V plus minus. Well, water has attributes of both a positive ion and a negative end, has a plus and negative end. So if you bring two water molecules in the right orientation, you will get an electrostatic attraction like ionic compound that happens naturally between the plus end and the negative end of another molecule. And this is what then just happens just naturally. And it's the same kind of attraction as an ionic bond, but it's between the molecules, not atoms. Okay, this electrostatic attraction is called a dipole-dipole interaction, and it's between polar molecules. And this is why water forms a liquid so easily and a solid fairly easily. See, all polar molecules will interact like this given the right situation. So if you put glucose, which is a polar molecule, in water, it will interact with water through dipole-dipole. Like this. The plus end will line up with the negative end, and it will form a dipole-dipole interaction. So it will dissolve in water. All polar substances will dissolve in water because water is polar, and polar molecules interact with each other, forming dipole-dipoles. So polar molecules, because they can interact with water, which is polar, are also called hydrophilic, which means water-loving. Okay, now slightly different case. So let's say you take an ionic compound and put it in water. Now, ionic compounds are not polar, but they dissolve in water. So why do they do that? Well, similar reasons. When you put NaCl into water, what happens is the positive ion will interact with the negative part of water, and it'll form an electrostatic attraction. So when you have electrostatic attraction between an ion and a polar molecule, that is called an ion dipole. Now don't mix this up with dipole-dipole, which is just between two polar molecules, or ionic bond, which is between two ions. All right, now let's go to nonpolar molecules. Okay. So you probably all know that carbon dioxide is a gas and methane is a gas. It's known as natural gas. Both gases are room temperature. Okay, nitrogen, N2, oxygen, O2, they're also gases at room temperature, are the main components of air. Okay, when we look at each of these molecules' polarity, we did these, CO2 and CH4, and your homework, you'll figure out that these are also nonpolar, that all of these molecules are nonpolar. So there's a real relationship between these guys being nonpolar and gases. Oh yes. Nonpolar molecules don't have plus and minus ends, so they don't have a natural attraction to each other. So it makes sense that they won't interact with each other and they just float around and not attract each other. Okay? So most gases at room temperature are going to be nonpolar. Okay. All right, now let's look at dry ice. Okay, dry ice, maybe you've probably seen it all before. Kind of looks like this. It just looks like clumps of ice, clumps of white hard stuff. It's smoking. It's that smoke at haunted houses and concert. It's opaque, which means you can't see through it. It's very cold. That's why it's like ice. Why it gives off smoke, gas, is because it doesn't melt. Okay, it doesn't turn into a solid. It actually goes from a solid to a gas. Okay, so it skips going from a solid to a liquid to a gas. And this straight going from a solid to a gas is called sublimation. And this is why we call it dry, because when you touch it, it doesn't leave your hand wet. Okay, that's because there's no wetness. It just is turning into a gas. Well, what is dry ice? It's simply carbon dioxide. So carbon dioxide is a nonpolar molecule which do not have any natural attractions towards other carbon dioxide molecules. But in this case, since it's a solid, that means the molecules must be interacting. So what's the deal? How can they be interacting even if they don't seem to have any natural attraction to each other? Okay. So it seems that carbon dioxide can have attractions. However, they don't happen naturally. Okay, so I don't want to go into a whole story behind this, okay? But it has to do with basically inducing charge, and you don't have to know that. But one of the things you want to do is that when you have polar molecules, nonpolar molecules, they can be enticed into liking each other. But it requires a bit of work to really get them to learn to like each other. To realize they like each other. They like each other, they do, but they don't know it. Okay. So let's see how dry ice is made. So the way that they make dry ice, there's two steps. So we're going to look at the first step. The first step is they take the carbon dioxide, and what they do is they physically cram the molecules close together. So how do they do this? So for example, let's say I have 8 carbon dioxide molecules in a given space, and they're all gas. So it's a gas. Here's your 8, floating around, banging against the wall, not interacting with each other. So how can I get them to realize they like each other? Well, what you do is you cram them together. One way to do that is you physically push them together with pressure. So now they're closer together. And once they get close together, they realize they like each other. That's key. Another way that's similar to this is that you can just make the volume that they're in smaller. And when you do that, they naturally have to get closer together. Okay, another way to do it is just add more particles. If you have more particles, there's going to be more interacting, more bumping into each other. Okay, and what you want to do is you want to have a lot of bumping into each other so that they realize they like each other. And if possible, you can't do it with carbon dioxide, but if you have big particles, okay, you don't have to cram them together because they're all kind of crammed together. So for carbon dioxide, what they do is they increase the pressure, and they actually increase the number of particles so that they can get a lot of interactions. And when there's a lot of banging into each other. Okay. When there's a lot of banging around into each other, they realize that they like each other. And when they realize they like each other, they stick together. Now, the stick together is actually similar to dipole, but we don't want to get into it here. We'll just say the particular type when they stick together, what causes them to stick together is something called London dispersion forces, or LDF. So what holds nonpolar molecules together are London dispersion forces. Individually, the individual interactions between the particles are very, very weak, but collectively they are very, very strong. Places where you'll see this, tape. So the reason why tape sticks is because when you add the tape to something, it's causing London dispersion forces between nonpolar parts. Now there's another step for turning dry ice and other things, which I could second into and going from a gas to a solid or a liquid, is that you decrease the temperature. And when you decrease the temperature, the particles slow down, so they're forced to see each other and interact and realize they like each other. This is also how they make liquid oxygen and liquid propane. So what they do is they take oxygen gas, they shove all the particles together, they decrease the temperature, and then you have liquid oxygen. Okay, like when you find in your oxygen tanks or in your liquid propane. So when you buy propane tanks, it's actually a liquid inside the container. They took propane gas and they turned it into a liquid by doing the things I just said. And then when you release the valve, there's no longer pressure holding those particles together, and it turns back into a gas. And the gas is what you ignite or you breathe in terms of oxygen. Okay, finally, what happens when you mix the two together? All right, nonpolar interactions. Do they mix? Well, here's an example. An example is oil and water. Oil and water don't mix. Oil is nonpolar liquid and water is a polar liquid. Now, this is kind of the way to look at it first of all. When a liquid substance doesn't mix in a liquid water, the substance is called hydrophobic, meaning it doesn't like water or hates water. And that's what oil does. So oil doesn't mix with water, so we call it hydrophobic. And we're going to see that this is actually not a good name for what's going on here. However, nonpolar liquids mix with each other, just like polar liquids mix with each other. For instance, gasoline and oil are both nonpolar, and if you have some oil on, like on anything, like on your hands or on a piece of metal or whatever, and you want to get it off of them, you just add gasoline, and the gasoline would dissolve the water. Now, the oil. Now, if you added water to the oil, it would not do that. Okay. So nonpolar dissolves nonpolar. One way. Here's an interesting one. So when you eat hot sauce, okay, hot sauce is the thing that makes hot sauce are the oils of the of the seeds. Okay. Now, if you heat some hot sauce and it's really really hot, and you want to get that hot off your face, okay, off your mouth, or off your tongue. If you add water, it's not going to work because water is polar and the oils of the seeds are nonpolar, and so in fact it'll make it even worse. Okay, because it'll actually make it the oil's more concentrated. So what you got to do is you have to put something in your mouth that's nonpolar that will take away the nonpolar oils. And one way to do that is eat something that has fat on it, like milk or ice cream. Okay, those both have a lot of fat on it, and fat is nonpolar. So eating the nonpolar ice cream or milk is going to dissolve the hot, okay, oils from the seeds and make it less hot. Okay, there you go. Now, now it looks like water and oil don't like each other, and so they look like they hate each other and want to avoid each other. So that's the hydrophobic bit. Okay, as a general description, this is okay, but it's not really what's happening. So let's look at why oil and water don't mix. Okay, suppose there's a container with 1,000 water molecules. All the molecules are attracted to each other, and there are a lot of dipole interaction. So there's a lot of water molecules, and they all want to see each other and connect up with each other. They just naturally want to do it. Now let's suppose we take 10 oil molecules and drop them right in the center of the water. What is going to happen? Okay. Well, this is what's going to happen. The water molecules are interested with each other and neither like or dislike oil molecules. So when you put the oil in the water, what the water is going to do is it's going to try to connect with itself, other water molecules. Okay, and that's the key thing here. So when you do this, when the oil gets put in the water, the water molecule will start to force the oil molecules together. This is so that the water molecules can get close to each other and interact to dipole-dipole. Now they don't, and this is kind of a way to think about it, they don't come up to the oil droplets and say, "Get the heck out of my way, I hate you." What they do is they kind of say, "Excuse me, I'm trying to see my friend. Here, can I get by?" And as they do that, there's no hating here, okay? So, and as they do that, they gently start to push all the nonpolar molecules together. Okay, and this shoving together of the nonpolar molecule causes them to realize they like each other. Remember? What we said is to have nonpolar molecules realize they like each other, they need to get shoved together. But what did water just do? Water shoved together the nonpolar molecules so the water molecules interact with each other. Well, what did this do? It causes the London dispersion force interactions to increase between nonpolar molecules, and the nonpolar molecules all want to stick together and stay together. So water has inadvertently helped the oil molecules realize they liked each other by having the water molecules trying to get to each other. Hey, that's pretty cool, isn't it? All right. So that finishes up the final PowerPoint of this semester. So I will send out a worksheet, and that will go over this, and hopefully you'll pick up on it, and we'll finish off the semester with a big bang. Okay. All right. Take it easy.